Okay, so in this particular problem, I have a few MCQ for you to watch and hopefully practice here. The first one is this particular solid cylinder is rolling down a ramp. The length of the ramp is 1 meter, and then the angle of the ramp is 30 degrees based on the wording, and the mass given here is 2 kilograms. All right, and it wants us to find the speed, the linear speed at the bottom of the ramp. So I'm just gonna go ahead and start this by using conservation energy. On the left side, you have all the KE and PE initially. On the right side, you have all the KE and PE in the final frame at the very bottom of the ramp. I'm gonna cross things out that does not exist though. So if you want, you can start, leaving stuff out just by recognizing the scenario given to you. It's release from rest, therefore it's not moving. If it's not moving, it doesn't have a linear KE, and if it's not moving, it's not rotating. So therefore KE rod is also 0. On the right side of the function though, I'm gonna cross out PE final due to gravity because that's height dependent. There's no height here at the very bottom of the ramp, so if H is 0, then PE is 0. All right, let's expand PE. PE by definition is just mass times gravity times the height that it's at, and then KE linear is just 1/2 mv square, and KE rod similarly analogous to KE linear here is just 1/2, but instead of mass is moment of inertia, instead of V linear is angular speed square. I'm gonna go ahead and substitute out I and omega because I need to find V. Right, so the question ultimately asks us to find V. So I have a V term here. I need to get rid of I and omega just so that I have V in both terms so I can factor things out. All right. So here, left side remains the same. The 1/2 K linear stays the same. The only thing I want to break up is I, moment of inertia. Generically, the function for moment of inertia is the coefficient, aka C here, times the mass times the radius square. So C here can be found using a chart on the World Wide Web. All right. Omega though is by definition V over R, but you notice here I substitute out omega, which is V over R, but outside of that, in parentheses, I have a square here because the square needs to get carried down. Well, this exponent's outside, so I'm going to distribute that to the V and also to the R on the bottom. So if you do that properly, things will cancel out. All right, so you notice here in my work, I have M highlighted all in yellow. That's because, well, there's an M in every single term here, so that cancels out. So in my next work, I'm not going to go ahead and, well, I'm going to go ahead and leave M out because it cancels out. So on the left side, it's just purely GH. The second term here is just 1/2 V square. And then because M cancels out and the R square will cancel out because, again, the exponent here gets distributed to the R on the bottom, so that's R square. You have an R square on top and R square on the bottom, that cancels out. And that'll just leave you with 1/2 C V square, whatever C is, right? Different shapes are allowed to roll down and different shapes have different C's. So I'm going to go ahead and just derive an expression for you here or derive an expression of V in terms of H. And hopefully you can use this for future references. All right. So here on the right side, you have 1/2 V square. On this side, you also have 1/2 CV square. Both these terms have a 1/2 and a V square. So I'm just going to go ahead and factor out common terms. So hopefully keep up with the algebra here. Well, if you factor out 1/2 V square, this is just a 1 right here where my cursor is for that term. And then if you factor out 1/2 V squared, the only thing left here is just a C. And that's why there's a 1 plus C in parentheses. Okay. All right, so from here, I'm just going to go ahead and isolate for V square by multiplying both sides by 2. And at the same time, dividing the 1 plus C because all this is in parentheses. So that's just a single term inside of a parentheses. Okay. All right, so multiply both sides by 2, divide both sides by 1 plus C altogether. All right, so therefore, I'm just going to go ahead and have this general expression, but this is V square. So to get V by itself, square root both sides. So really, generically, the function for linear speed at the bottom of the ramp or after some sort of height is 2gh, whatever this h is, okay? So if you go from top to bottom, this height would be the whole entire height. Well, what if you only go half the height? Then this height here would just be half the height. So however much it dropped. So keep that in mind. So don't just plug in, height just because the problem said so. Make sure you recognize how much height has been dropped, quote unquote, change. All right. So this is the generic function. If you're currently a physics student, this is super useful. If you've seen my work and you know how I got here, you can probably just start using this just because there's no need to prove it all the time. Okay. So this is the linear speed after the object has rolled down some height. All right. So now I'm just going to use it. Okay. Well, how do I use this? Well, I don't know what h is in this particular problem. The problem gives you the angle and it also gives you the length of the ramp. So to find h is just the hypotenuse times sine of theta. It's sine because h is the opposite leg of this particular ramp. So I'm just going to go ahead and substitute out h. So instead of h, I'm just going to say it's 2g L times sine of theta. And now I'm just going to plug in stuff that I know. Okay. The problem states that you want to use G as 10 meters per second square. I think they just want to keep all these answers nice. So instead of having like a decimal, 10 is just a nice number. Okay. The length is given as 1. That's 1 meter there. And then sine of 30 degrees. Okay. And sine of 30 is just a half. And then the coefficient for a solid cylinder rotating about a center of mass is just 1/2. That's where this 1/2 is from. Now, if you just do basic algebra here, just clean up the bottom a little bit. So 1 plus 1/2 is 3/2. That's where the 3/2 here is from. Okay. Now, 2 times 10 is 20. 20 times 1 is 20. 20 times sine of 30, which is a half. So 20 times a half is 10. So that's where there's a 10 there. And on the bottom is 3/2 because 1.5 is just 3/2. But you notice here you have a 10 and you're dividing by a fraction. So algebraically, if your denominator is a fraction, then you multiply by the reciprocal just so you can write it nicely. So if you flip the 3 over 2 to 2 over 3, 10 times 2 is 20, and then the 3 remains. So that matches with the answer choice B. All right, let's move on. And the next one here, similarly, you have a solid cylinder, angle's 30 degrees, and then it wants you to find the acceleration, though, of the cylinder. Okay, so here are the answer choices listed. All right, let's go and crack this one out. So to do this one, I'm just going to start with the common form in your kinematics day. The acceleration here is constant, so I can apply this particular function. Vi is 0 because it says it's released from rest. Now, so therefore, the one thing I do need is Vf, and I need delta x, right? And delta x is just the length of the ram here, and Vf I don't know. So I'm just going to run through it one more time in case you didn't keep up. To start, set up conservation energy, PE equals to KE linear plus KE rod. So here, I made the statement just like the previous slide. I'm going to go ahead and expand I again to CMR square. And then here, I'm just going to keep omega square for now. And then as you can see, M cancels out as the previous one. So keep that in mind. The mass of the object doesn't really matter for these types of problem, okay? If you're just trying to find A, if you're just trying to find V, the mass doesn't really matter. All right, and similarly to the last slide, omega square can be broken up into V square over R square. I went ahead and just distributed the exponent to V and R for you. And then the R square is going to cancel out once again. So the second thing I like to point out here is that the radius of the shape does not matter. Okay, it's the coefficient of the shape that matters a lot. As you can see here, there's a C that's highlighted, and if you kept up with the previous problem, C remained in the velocity function. Okay, I'm just gonna go ahead and clean this up on the right side a little bit, and then here once again we can factor out 1/2 V square and blah blah blah. You can solve for V square. However, I'm just gonna pause here. Okay, I'm just gonna keep this as V square as 2GH 1 plus C. Well, I don't want to square root this term because in my acceleration function, I need VF square. Well, this is my VF function here at the bottom of the ramp, okay? So I'm just going to substitute it in. So A is equal to VF square, but VF square itself is 2GH over 1 plus C. And then the 2 delta X just gets carried down, okay? Now I can just do a little more, okay? Here, you have 2GH over 1 plus C divided by 2 delta X. So your numerator here is a fraction. If your numerator is a fraction and your denominator is a whole, you have to visualize putting a 1 underneath this 2 delta X. Okay, hopefully they taught you that in grade school. So if the denominator is just a whole term, just put it over a 1 because dividing anything by a 1 doesn't change itself. But now you have a fraction, 2 delta X over 1. Now you just have to multiply that by the reciprocal. So that's what my work looks like here. So the top fraction gets carried down, except the denominator is now 1 over 2x instead, right? So instead of saying 2x, 2 delta x over 1, you divide by a fraction, so you just multiply by the reciprocal, which is 1 over 2 delta x. All right, hopefully your basic algebra skills on here. The 2 is going to cancel out, the 2 on top is going to cancel out, and then if you think about it, this is just GH times 1, which is just GH. And then on the bottom here, you have 1 plus C in parentheses times delta X. So I'm just going to clean this up a little farther. All right. Well, what is H? H by definition here is the opposite leg of this particular ramp. So we can say sine of theta, whatever theta is equal to opposite over hypotenuse, which is X. So that's where the statement comes in. Sine of theta is equal to opposite over height being X here. And then we need to find what h is. Well, to find h, multiply both sides by x. That's why this statement is true. X times sine of theta is the height of the ramp. Okay, so I'm going to go ahead and substitute out h. So instead of h, I can just say it's just g, just carry down. H is x times sine of theta. All right. And then on the second parenthesis here is just 1 over delta x. But as you can see here, there's an x on top and then x on bottom. I know this doesn't have the delta time, but really, if you think about it, it's just the same thing. Okay, the length of the ramp is what matters here. All right, so x on top, x on bottom cancels out. So this is just a 1 divided by a 1, which is now insignificant. So the only thing you have left is g sine theta over 1 plus c. Okay, so this is your generic acceleration function for these types of problems that's allowed to roll down the ramp. The only difference here is you got to pay attention to your coefficient for the moment of inertia, because every shape has a different c, and if it has a different c, then it's going to have a different acceleration down the ramp. All right, so I'm going to suggest that you highlight that in your work, write it down, say it's important. I've done the proof for you here already, so you can just use it unless you like to prove stuff. Or I would suggest just taking a couple minutes out and doing it for yourself, just so you're really good at this in case you have to ask to prove anything on midterms and finals. All right. So now that I have that, I'm just going to go ahead and apply it here, g sine theta. But this is a solid cylinder, so the coefficient for a solid cylinder by its axis of rotation through the center is 1/2. 1 plus 1/2 is 3/2, and the numerator stays the same. But here again, you have a numerator divided by a fraction, so you would multiply by the reciprocal. So therefore 3 over 2 gets flipped upside down, would be 2/3. G sine, well, the angle here is 30 because it said so in the problem. And then if you know your unit circle, great. If not, use a calculator. Sine of 30 here, this is 30 degrees. Sine is equivalent to your y coordinate system, so sine of 30 is just a half. Well, sine 30 can now be replaced with a half, so I'm just going to rewrite 2/3 g. Instead of saying sine 30, I'm just going to write a half. As you can see, the 2 on the top, 2 on the bottom cancels out. So the answer is now just 1/3 g. Okay, and let's see, that matches B. 1/3 g is the same as saying g over 3, and that's that for that one. Okay, last one of in this particular video. So here we have a hollow sphere though, right? So the last couple of examples have been solid cylinder. It doesn't really matter. Pay attention to the shape. Here we have a hollow sphere. It rolls down some ramp, and it wants us to find the angular acceleration, aka alpha. And here are your choices. Well, to find angular acceleration, you have to know the relationship between linear acceleration and then angular acceleration, and that's just to multiply it by r. Okay, so here we say a is equal to r alpha. So the problem wants angular acceleration, so I'm just going to go ahead and isolate for angular acceleration by dividing both sides by r. Now, I already proved to you that the a function in the previous slide is g sine theta over 1 plus c. So I'm just going to use it. Okay. Divided by r, so I carried r in the denominator down. Well, I highlighted c here because you have to pay attention to the shape that's given to you in a given problem. A hollow sphere has a coefficient of 2/3 relative to the center of mass as it rolls down a ramp. Okay, so nothing changed except for the fact that I substitute out c for 2/3. Well, here I'm just going to clean it up a little bit. 1 plus 2/3 is the same as saying 3 over 3. So I highlight the 1 in yellow here because I can go ahead and rewrite 1 as 3 over 3 because the denominator here is 3. And when you add fractions, you have to have common denominator. So I'll make the 1 into 3 over 3 plus 2/3. Okay, so that's the only thing I've done here. Therefore, 3 plus 2 is 5. And the common denominator is 3. So it'd be 5 over 3. So I'm going to carry my work to the top right of the page here. So it would be g sine theta divided by 5 over 3 divided by r. Okay, this is where you just have to be really careful with how you denote stuff on your work. Dividing by a fraction here in the numerator is the same thing as multiplying by the reciprocal of 5 over 3, which is 3 over 5. Now I've turned the numerator into just 3 g sine theta divided by 5. The r on the bottom, I haven't done anything to it. Okay, so I'm just rewriting the numerator just so it looks a little cleaner. But now you have a fraction on the top divided by the denominator, r. Well, here's r by itself in the denominator. You can turn this into a fraction by simply saying r over 1 Therefore, you would multiply it by the reciprocal of that, so it'd be 1 over r. Okay, so I just rewrote the term on the top as 3g sine theta over 5. But instead of dividing by r, you can now multiply by 1 over r. Well, 3g sine theta times 1 is the same term. 5 times r is 5r. So therefore, it would just be 3g sine theta divided by 5. And that matches, let's see, which answer? D, okay? And that's that. I think you just have to be super careful about dividing fractions and stuff like that. So, all right, I hope that helps. Good luck. Stay nerdy. Don't be whack.